We recently published a correspondence in the Lancet that attempted to explain two different paradigms of modeling, a statistical approach and a mechanistic approach. We wrote this in response to a letter that incorrectly assumed that our model did not account for patients that are removed from the waiting list without being treated. This is a fascinating conversation to have in a clinical journal, but I think many practitioners can get this wrong. Understanding the difference between a mechanistic approach and a statistical approach is fundamental, especially for those who use computational techniques such as data science, statistics, machine learning in healthcare. Although we try to explain the difference between these two approaches in our correspondence, I don't think that 400 words do justice to this topic. Therefore, in the next few minutes, I will try to explain the difference between the two approaches, and I hope that you will walk away with crystal clarity and also see why the approach we took, the machine learning inspired approach, why that is just amazing. Let's begin with some basics first. Mechanistic Models 101. Mechanistic models are based on the underlying biological, chemical, physical, or social processes that govern the system being studied. They aim to represent the actual mechanisms and relationships within the system. Some of the key characteristics of mechanistic models are: they are theory-driven, so they are built on theoretical knowledge about how the system works. These models often include detailed representations of processes and interactions. And the parameters and mechanistic models typically have physical or biological meaning and can be measured or estimated from experiments. Statistical models, also known as data-driven models, rely on observed data to infer relationships and predict outcomes. They use statistical techniques to identify patterns and associations in the data without necessarily understanding the underlying mechanisms. Some of the key characteristics of statistical models are: first, they are data-driven, so they are built using historical data and statistical methods. These models often use simpler representations, focusing on correlations and patterns rather than detailed processes. And the parameters in statistical models are estimated from data and often do not have a direct physical or biological interpretation. So the key differences in these two approaches are: in terms of foundation, mechanistic models are based on theoretical understanding of processes, while statistical models are based on empirical data and statistical relationships. In terms of complexity, mechanistic models are often more complex, detailed, and specific to the system being modeled, while statistical models are generally simpler, focusing on patterns in data. In terms of interpretability, in mechanistic models, the parameters have clear physical or biological meaning, while in statistical models, the parameters are often abstract and primarily used for prediction rather than understanding. In terms of data requirements, mechanistic models will require detailed knowledge and data about the system's processes, while statistical models rely heavily on the availability of high-quality historical data. Let's go to the letter published by Mark Wood, who states that Syed Ahmed Shah and colleagues project the post-pandemic elective care waiting list in England's National Health Service using a compartmental model through which various scenarios of referral inflows and treatment outflows are simulated. However, their model does not account for the outflow of patients who leave the waiting list before treatment. This is not correct, and we have already responded to this, where we stated that we disagree that this important dynamic was neglected in our model. We took a statistical approach with the use of a vector autoregressive model for 3 linked monthly time series. Richard further alludes to their previous work to show that it is possible to include additional terms when needed. The previous work that Richard refers to, published in Healthcare Management Science, includes an explicit term to account for patients that leave without being treated. The model they have is formulated as a set of differential equations which is then solved and subsequently used for projections. The statistical approach we took can be represented with a simple model with 2 flows, an inflow denoting demand and an outflow denoting patients that are removed from the system. At any given point in time, the total number of patients waiting depend on both the inflow, the outflow, and the number of people that have been waiting in the past. We have formulated this with an equation that includes a term for inflow and a term for outflow with coefficients that are unknown, and we then use all the historical data that is available to us, and then we find the values of the coefficients that best describes this data, and we use a technique called maximum likelihood. This is exactly what we do in machine learning. We formulate a problem with a generic equation with some unknown parameter values, and then we use all the past data and some kind of an optimization technique to find the best values of those parameters that can explain the past data. Our approach is the very essence of how problems are solved using the paradigm of machine learning. When you are designing a spam filter, you don't write explicit rules to define what a spam email looks like. Rather, you feed in lots of examples of emails that are spam and emails that are not spam, and then you feed it into a model and you let that model learn to differentiate between spam and not spam implicitly. In other words, it just learns the rules implicitly. This approach, where the rules are learned from the data rather than writing the rules explicitly, is the very definition of machine learning that was proposed back in 1959. In our approach, we provide all the past data of patient waiting, inflow and outflow, and then we let the model learn the dynamics of the system implicitly. There is no need to have explicit terms for every internal process that happens within the system, such as if a patient enters the system, that is, they are added to the waiting list, but then eventually they are removed for reasons other than being treated, such as treatment not needed, or they go private, or in the case of death. The reason you don't need these explicit terms is because the coefficients that we learn for inflow and outflow, they will automatically adjust for everything that's happening within the system to make sure that the total number of patients waiting at the end of each period when you are learning the model is correct. The key thing is to ensure that whatever definition you are using for inflow and outflow, you use the same definition when you are using the model for making predictions. As long as you are consistent, this model will work well. To further drive this concept home, here is a quick example to demonstrate how robust our system is. The coefficients learned will automatically adjust, allowing the model to adapt to any healthcare system as long as you have one time series for inflow and one time series for outflow. A comparable data that is publicly available is from Public Health Scotland. Luckily, apart from showing the number of patients that are removed every quarter, the time series provided by PHS, it actually provides a breakdown of the patients removed. So all the patients that are removed from the system, it's a combination of patients who are treated, which is roughly 80 to 85%, but there are other reasons why patients might be removed, which include reasons such as they are referred back to GP or primary care, transfer, treatment no longer required, or other reasons which could include death as well. Now, if we apply our model to this data and use the total removed from the waiting list as the outflow time series, the coefficients we get are 0.998 for inflow and minus 0.998 for outflow. Now assume that we don't know the total removed, but only the total that are treated and hence removed, which would be about 80-85%. If we apply our model, but use the total treated as the outflow time series, the same model, so just the two flows, inflow and outflow, the coefficient we get now are 1.090 for inflow and minus 1.246 for outflow. So let's work out the change in waiting list in a given time period, assuming that we have an inflow of 100 patients and an outflow of 100 patients using these two approaches that I just described. Based on our first model, the change in the waiting list will be 0, because it would be 0.998 multiplied by 100 minus 0.998 multiplied by 100, which will give you 0. Based on our second model though, the change in waiting list in the same scenario would be a reduction of 15.6. That is 1.09 multiplied by 100 minus 1.246 multiplied by 100, which gives a minus 15.6. In other words, the second approach is telling us that even when 100 patients are added and 100 patients are treated, the net effect on the waiting list is a reduction of 15.6 rather than 0. This 15.6 reduction in the waiting list happens because patients are removed from the system for all reasons other than being treated, which has implicitly been taken care of, even though we only use the total treated as the outflow time series during training. And that is the beauty of our approach. There is absolutely no need to explicitly model the internal dynamics of the system in detail. As long as you have a time series for inflow, a time series for outflow, and a time series for the number of patients waiting, our approach will automatically learn the internal dynamics of the system implicitly and effectively predict future waiting size. This idea is exactly why machine learning started to take off since the 90s, when we learned that we don't have to explicitly write rules and model systems in detail. Instead, if we have a flexible model and if we can feed in enough data, most of those rules will be learned implicitly, and we can use such a model for making reliable predictions. What's even better, this approach is not tied to any healthcare system. It's flexible and robust, and as long as the internal dynamics of a system which generated the data, if they stay consistent, the model that you will end up learning will be able to make reliable predictions. In summary, our approach not only simplifies the modeling process, but it also delivers data-driven predictions that can adapt to various systems. Hopefully, the distinction between a mechanistic approach and a statistical or a machine learning approach is crystal clear to you now. Thank you.